a lot of people here in the audience who are much better at physics, who are involved in physics education research, and who know a lot better how to convey the concepts to students than I do. So in putting this together, I thought I should be a little pedagogical, but what I finally decided is that I would focus on the science, what I know, the science, construction, and operation, and try and, you know, as a professor, sort of give you little highlights, what I think are connections to undergraduate physics as I go along. And maybe I'll learn something from you as to how to sort of incorporate this into teaching. So I really like this description of IceCube. So Popular Mechanics had a story several years ago when we were first starting the construction of IceCube about what were going to be the next 10 biggest things in astronomy, and I think they came up with the best description of IceCube I've seen. It says, like all humans, science are capable of seemingly absurd and futile. Consider the construction ongoing of the IceCube telescope. Using a 5-megawatt jet of hot water, technicians are melted 2-foot wide holes 1.5 miles into the Antarctic ice in the Amundsen and Scott South Pole Station. Before the water refreezes, they insert a cable strung like a set of Christmas tree lights with a globular camera housing. By the time the technicians are done in 2010, and we did finish on time, IceCube's 80 vertical strings will adorn a cubic kilometer of ice from 1.4 kilometers down to 2.4 kilometers. In other words, it's 4,800 cameras looking at solid black ice. On the scientific absurdity scale, this ranks up there with studying acuity, doesn't it? And it says, no, admittedly, one of the weirdest machines on this list, IceCube is also the most, potentially the most revolutionary because it's going after an astronomical quarry, much like LIGO, that's never been studied before, and that is the cosmic neutrinos. And that was brought up in some of the talks yesterday. We were talking about really, you can look at the sky, you can look at the optical, you can look at all these other opticals, other octaves in the electromagnetic spectrum, but then, as we've heard, you can also look at neutrinos, protons, gravitational waves. There's all these other things that are going to give you additional complementary views and pictures of the universe, and hopefully IceCube will give us some surprises. So I know that this has sort of been gone over a little bit by Grace's talk, but I like to kind of take a historical perspective. And in my view, the IceCube sort of began with Victor Hatz. And I like this because I think it illustrates to students something about the spirit of what science is really like. He really thought he knew the answers. He wanted to know where radiation was coming from, and at the time, thought was it must be just radioactive elements in the rocks and stuff in the earth. And so he had to test this hypothesis. And of course, if radiation was coming from all the rocks and stuff in the earth, surely if you got in the moon and it got really great, you went up to 5 kilometers, went out onto the moon, then you would see a decrease in the amount of radiation as you went up higher and higher. Well, he was very brave and he actually did this. And that's not what he found. He actually found that as he went higher and higher, that the radiation levels didn't necessarily decrease with altitude. So that was really the first cue that we got that cosmic rays were hitting our atmosphere. So I think that science is really about the unexpected. It's really about exploration. Whereas so many students think that science is a bunch of facts that they memorize out of a textbook. So I had one student who was a PhD student of mine who had just came to graduate school after just retiring after 20 years in the Navy. And he said, oh, well, in the Navy, I kind of knew what I was going to do every day. You know, there was this certainty, there was this protocol, you know, and he says, you know, this makes me really uncomfortable because I come in and he says, I don't really know what I'm supposed to be doing or what, you know, what's going on. I said, well, that's research. Yeah. Research is open to surprises, and we certainly hope that IceCube will see some. So, of course, the next chapter in this story, which Greg kind of covered, is Pierre Auger, and so, not the observatory, but the man that the observatory was named for. And so he put some particle detectors up at very high altitudes, and he was the first to sort of see these extensive air showers that Greg was referring to. So when these cosmic rays hit the atmosphere, there's these, you know, as Greg said, these particles destroyed. There's a shower of pions decaying to muons and neutrinos and all these different kinds of particles that are showering down on our Earth all the time. And by seeing that two of these detectors that were very far apart were both lining up in coincidence, that was the first clue that these were really large air showers of very high energy particles. And of course, the picture as we see it today is this picture that's been shown several times already. But one thing I would like to point out about this picture that I don't think anybody has mentioned before is that one way of sort of conceptualizing for students and letting them know what kind of energies we're really dealing with by talking about something that they're kind of familiar with, although this was a little last week at first because I'm a girl and I'm not a sports fan. But the kinetic energy of these highest energy particles that we're seeing actually are in excess of a professional baseball pitch. And again, being a girl, I didn't really know how fast a professional baseball pitch was, or how heavy a professional baseball was, a baseball was. So one of my male colleagues actually did a back of the envelope calculation on the chalkboard that shows me that in fact this kinetic energy is comparable to a professional baseball pitch. And if you think about something coming, a subatomic particle coming from somewhere out in the universe that has that kind of mind-boggling energies, it has to be tantalizing, it has to be interesting, and it's something that we certainly want to start to understand. And I think that one way that sort of illustrative thing that plot that for me, which I think that any sort of undergraduate who knows anything about magnetic fields can sort of understand is what's called the soulless plot. So, you think that in order to get such high energy, the particle has to be confined in some very energetic area, like, for example, in falling near a black hole or something, for a very long time in order to be accelerated to these energies. So it has to be confined to that area, so you need some magnetic field. And of course, we all know that the radius of curvature gets tighter and tighter as you go to lower energies, and so for very high energy particles you need a very large size. So what we're seeing is size of an object on this area, and we see magnetic fields on this area. And being a particle physicist, I would really like to talk to some of you astronomers and understand how you actually nail down these values. But this shows size versus magnetic field. You would need to confine something in an area, and these are lines of constant energy. So you see protons at 100 eeV, which is 10 to the 18 electron volt. Protons at 1 zeeV, so that's another 3 orders of magnitude higher. Here's iron at 100 eeV. Of course, iron is different because iron, if you assume it's an ion and not a proton, iron has a much higher Z, it has much higher charge, so you get more bang for your buck with an ion. So you can plot on this scale all these different astronomical objects according to their size and their magnetic fields, and you can see by where they follow these plots which one of these things would be candidate accelerators. So anything above this line could be accelerating protons to 1 zeeV, so there's not much above the line. And down here on the 100 eeV scale, you see various things like Greg's already mentioned active galaxies, and he's touched a little bit on GRBs. You can see that down here, a little lower supernova remnants would be responsible. But this is sort of like nice freshman or sophomore physics you can use in just sort of eliminating or determining what would be good candidates for these accelerators. So candidate sources below the knee. So this is was already shown. This particular, I think this is Brian's supernova remnant was already shown yesterday. So below the knee, it was already explained that these shock fronts can actually be accelerating particles in these galactic supernova remnants. And then, of course, we heard from Greg today about active galactic nuclei being a very tantalizing source of cosmic rays. And gamma ray bursts were also touched on, but gamma ray bursts are really fascinating because this is a transient phenomenon. They last on the order of seconds, or at least the majority of the energy can be released in the order of seconds. And in that time, they can release something on the order of several solar masses. So these are really interesting phenomena that again, really release mind-boggling energies in a very, very short time. So this is sort of the picture, the same picture we've seen before, but annotated with some of these various objects. So, below this need, which Greg pointed out, supernova remnants could actually explain some of what we're seeing. Above the need, things have to be coming from outside of our galaxy because the galactic magnetic field of our galaxy can't actually contain it. In the middle, there's some transition, who knows what's happening, and that's really sort of the area that IceCube is going after. So IceCube is a neutrino telescope. So we've heard about gamma rays yesterday, and we've heard about protons today. Those each have their limitations. So primarily, Auger is going after very high energy protons, and the reason is that at lower energies, protons can be bent by this intergalactic or interstellar magnetic field. And as Greg mentioned, that even at high energy, there's some deflection, but they focus on higher energies because they get stiffer track. So protons don't necessarily point back to their source. They do more so at high energy, but not always. Gamma rays can point back to their source, but as we know, there's this pervasive cosmic microwave background throughout the galaxy, and once you get something that's energetic enough that it's above the pair production threshold, that's going to limit your horizon. And even protons, as Greg mentioned, the GZK cutoff, there's a point at which protons are you can actually have protons produce pions or delta resonances on this cosmic microwave background, and you'll see this steepening of the proton spectrum, and that even limits the horizon over which you would expect to see protons. So the solution, which is not an easy solution, it's a little bit draconian, is that you could actually look for neutrinos, which sounds like a great idea. So neutrinos only interact weakly, and they don't have any electromagnetic interactions, so they can go directly through magnetic fields and reach us on Earth, and they will point right back to their source, if we can see them, which is the hard part. Okay, so neutrinos, in a way, are the ideal messenger. Of course, the very thing that makes them the ideal messenger also makes them very hard to detect. So if we look at a plot of the various messenger particles, you can sort of see here the horizons. So the area that's blacked out is the area that you can't actually see. So we have you have photons getting absorbed on the cosmic microwave background. You have protons, again at very high energies, being attenuated. And also shown on this plot, so this is the observable distance as a function of energy. You can also see an astronomical scale. So this is how far you would need to see. This is the region, the size of our galaxy. This is to the local group, nearby clusters, AG and cosmology. So if you really want to look very far out, or equivalently very far back in time, it seems like neutrinos could be a really good messenger for doing that. Of course, now as I alluded to, the reason neutrinos are the ideal messengers is because they only interact weakly. And so the only way that you can actually see a neutrino, so you never see a neutrino directly, of course, is by its interaction. So what happens is a neutrino gets captured on a nucleus, and in a diagram that's very much like beta decay except rotated on its side, it gets captured and then transmutes a proton to a neutron or a neutron to a proton, depending on whether it's an antineutrino or a neutrino, and out comes an electron. So this is very much like I say, it's beta decay except turned sideways. So in comes your neutrino, out comes your electron, muon, or tau. And what's happening on a particle physics level is that all forces are mediated by some particle, and the mediator in this case is a W, or an electroweak photon, which is of course very heavy, or a Z. So these are 80 and 90 GeV respectively. So one connection you can make in sort of conceptually explaining to students why it is that this is such a weak force is that you can think of these W and Z photons that are being exchanged as being virtual particles. And the Heisenberg uncertainty principle tells us how long those particles can survive. And so that really decreases the probability that this neutrino can speak to these particles in the detection medium. And another interesting thing about neutrinos is their discovery. Their discovery was based on simple conservation of momentum. Some people looked at beta decay, and they measured the energy of the particles involved in beta decay before and after, and realized, the momentum, and realized that there was a momentum imbalance, and so Pauli postulated that there had to be some invisible particle that was taking away some of the momentum from this interaction. So it's simple, in essence, first year of physics that allowed him to make this prediction that the neutrino must exist, and of course it was detected sometime later. So there's some amazing facts about neutrinos, that 40 billion neutrinos continuously hit every centimeter squared on the Earth from the sun 24 hours a day. Their interaction length is about a light year of steel. That's somewhat energy dependent. 1 out of 100 billion interact going through the Earth, so that kind of gives you an idea of what the challenge is for us. 300 million per cubic meter are left over from the Big Bang, and they only have a tiny mass, as we know. And as we've also discovered, and arguably one of the most exciting discoveries in particle physics in the last couple of decades, we found that they actually can change flavors from muon to electron neutrinos, or big switch between the different flavors. So what is it, you might ask, that neutrinos have to offer to sort of shed light on this cosmic ray mystery? If we really want to shed light on cosmic rays, we really want to know where the protons are coming from. And the reason is because anytime you have protons interacting the way they would in our atmosphere or with the cosmic microwave background, you expect that you would produce pions, and those pions in their decay chain would produce neutrinos. And so if you have some source that has some ambient photon field or dust or whatever material, it's hard to imagine that nature is accelerating these things in a vacuum. Those protons would then interact and produce pions. It's also worth noting that charged pions and neutral pions can be produced, and those neutral pions can produce gamma rays, and that is one way in which gamma ray astronomy and neutrino astronomy could be complementary to each other. The way we actually detect neutrinos is we have a target material so that the neutrino can interact, that target material also acts as a Cherenkov radiator, so it has to be something clear. So traditionally we've used water, and so of course everybody thinks of Amundsen and Scott flowing Cherenkov radiation. But this is very easy to understand for anybody who understands waves or a sonic boom or something. This is essentially, of course, the electromagnetic equivalent of a sonic boom. You have some material with an index of refraction, such that the velocity of the particle is less than the speed of light in vacuum, but the particle itself is going close to the speed of light in vacuum, and it actually outruns the particle, and so you have this wave front, just like a sonic boom following behind it. And that's the basic technique that's been used with Supermo and some of the other pioneering experiments in this field, and it's also the technique that IceCube uses. So to give you an idea for those of you who are familiar with Supermo and some of these other experiments, where IceCube is in this sort of neutrino scale. Here you have energy on this scale, and this is flux, so number of particles per unit area. So solar neutrinos are way down here. And here you can see Supernova 1987A. So you see relatively high flux and relatively low energy. What IceCube is going after is in this region that's boxed here in the red. So this is what you would expect from active galactic nuclei here in green. These are the GZK neutrinos, which are probably above IceCube's reach. Then gamma ray bursts here in purple. One thing that I'll touch on later is that one thing that makes this really challenging is that these same physical processes that are happening in the source are also happening in our atmosphere. So we're also being bathed in this radiation from the atmosphere. So these secondary particles that we're seeing from neutrino interactions in the ice are also happening in the atmosphere, and we have to distinguish those from these atmospheric interactions. And in fact, the atmosphere is even producing neutrinos. So this is the anatomy of the IceCube detector. So it's a simple tracking detector. You have the neutrino come in, it interacts, and the secondary particle then goes to our sort of artist conception of the ice, which is just sort of studded with photomultiplier tubes. And by seeing which one lights up first, we can actually track this through the ice. Now, the reason we didn't build this in a mine shaft or something like that with Super K is because we're going after these higher energies where the fluxes are dropping off. So we need a very large target volume, And it's just too costly to scale up any sort of a man-made reservoir. So we needed to go looking for a natural reservoir that we could use to build, because we were going after these very high energies where the fluxes were low. So where did we find our reservoir? We found our reservoir at the South Pole. And the South Pole actually has 330 million cubic kilometers of ice, which is 70% of the world's fresh water. It's all locked in the South Polar ice cap. So there's a glacier covering the South Pole that is 2,850 meters high. Because of the low atmospheric temperatures, the human body thinks that's actually about 3,200 meters. So it's really quite an acclimation if you get flown in there by plane, as we do, because of just, you get 50% of the oxygen you do at sea level. So it's higher than the Largora. And that's because that's just how thick the glacier is. But of course, the glacier is what we want. Even the highest temperature ever recorded there was about 8 degrees Fahrenheit, which is very unusual. Even in the height of the summer, a typical temperature would be more like -20. That's without the wind chill. It can get below -100 in the winter, so it's only accessible in the summer. So that's one of the real challenges in building IceCube, is that we had a very contracted building season every year. It is a desert, however, there's prevailing wind direction that brings snow in. The snow then gets compactified and eventually gets compactified into ice. And the deeper you go, the clearer the ice is, because you're pushing out the waves pushing out all the air bubbles and various things like that. The ice moves 10 meters a year. And so this is actually a glacier, it's flowing. And so it does seem to flow in lockstep, which would be bad news for IceCube if it didn't. And you can only come and go during the summer. We only have 1 day a year, which I don't know how many of my colleagues learned in PhDs see me in the summer here, saying, it's summer, shouldn't you be in the South Pole? And I have to point out to them, no, it's not summer. And all supplies, food, fuel, materials must be flown in and out by plane, and that is quite an expensive proposition. So I just wanted to mention that this year, and this is one, the whole polar exploration aspect is one thing that really captures students' imagination. But this year is the 100th anniversary of the expeditions of Amundsen and Scott to the South Pole. So Amundsen reached the pole on December 14th of 1911, which is the day I'm supposed to arrive at the pole this year. And of course Scott was a little behind him, and that was his demise. He got there January 17th and didn't make it back to safety before the temperatures really started dropping off. And so they were second, and his entire party passed away. But anyway, this year this austral summer marks the centennial And Greg mentioned during his talk that it was hard to get to Malargua, but it was harder to get to the South Pole. But compared to these guys, it's getting a lot easier. So this is what it looks like to get there these days. So if I'm moving from my home here in DC, we fly to Los Angeles, then to Auckland, and then from Auckland to Christchurch on all on commercial air. When you get to Christchurch, that's when the Air Force takes over, and we fly on the C-17 down to McMurdo, which is an island on Ross Island on the Ross Ice Shelf. And typically spend a night there in McMurdo, and then there's another 3-hour flight on a ski-equipped Hercules down to the up to the South Pole. So this is this past year. This is the C-17. It actually just lands out on the Ross Ice Shelf, and people. It doesn't stay there long. Passengers get off. They unload and offload your cargo, and takes off with the outgoing passengers. So they just literally land on this eastern area of the Ross Ice Shelf. And this is a picture of one of the ski-equipped Hercules planes that actually takes us down to the South Pole. So this is a prop plane. You can see the skis here on the plane. So once it gets to the South Pole, they just have bulldozers that bulldoze what they call the skiway to the South Pole and make a nice, firmly packed area for the plane to land. And these planes actually never cut off their engines when they get to the pole. Because they would be hard to restart. So they land, offload passengers and cargo. They siphon the fuel out of the tank. So the entire South Pole Station, all our operations there are run on jet fuel that's been siphoned out of the tank. That's the safest way to get it down there. And then they take off with passengers. And of course, there is no way into or out of the South Pole this time of year because first of all, it's pitch black. There's no way to see, and also the hydraulics on a plane I'm told will fail at about -50. So there's some rather spectacular scenery on the way down there. This is the Transantarctic Mountains as seen from the cockpit of the Herc. And this is a picture of some of the volcanic islands in the Ross Sea. IceCube design, construction, and performance. So we have this wonderful natural resource in a very hostile place, and we have to engineer a neutrino detector out of it. IceCube, we can see it. So the way we build IceCube is we drill holes in the ice that go almost down to the bedrock, just a few hundred meters before you hit the bedrock. And IceCube is called IceCube because we've instrumented a cubic kilometer, so it's a kilometer across. So the top part, the highest most photomultiplier tubes are 1.5 kilometers below the surface. That's to avoid the bubbles and also the getting plastered by cosmic ray muons. And so each one of these strings, which provide power, communications, and mechanical support, have 60 photomultiplier tubes on it, and they're on a 125-meter triangular grid. And one nice thing about IceCube, which is also true of OJ, is that unlike a particle detector where you're rolling it into a collision hall, we can take data with the partial detector as it is being built. So we have quite a few results already. We upscoped partway through the construction, and if I have time, I'll say something about that. And we have a more densely instrumented area in the center of the detector. And the reason is because these 125-meter grid actually gives you a lower energy threshold. You can't, because low energy muons would not live long enough to travel between strings. We can't. That decreases our threshold, and also because of background noise and various other things, it's very difficult to see low energy things with the IceCube detector. So the original design was to start to see neutrinos at about 1 TeV, but we have a more densely instrumented core in the center called the deep core, which is primarily aimed at seeing primarily aimed at seeing dark matter, which I'll explain. So anyway, as I say, we've been taking data continually, almost 100% lifetime over the last several years. We have a very high muon rate, and that is due to cosmic ray muons, and a relatively low neutrino rate. So we really have to beat down our background. We're really looking for a signal in a haystack, about 1 in a million events. So we completed the detector in December of 2010. It's working beautifully. It was on time. It was on budget. So we just hope for exciting things to come. So here's a picture of the construction of IceCube. This is the heating plant, all run on jet fuel. And here is a hose reel. So, and there's a person for scale standing next to the hose reel. And this is the area where the hole is actually being drilled. They built a little hut over it so we can't cut all our digits while working on it. So the hose gets strung over a winch and dropped directly down into the ice, and we have a high pressure hot water that actually drills the holes. So it takes, just quickly, it takes about 4,800 gallons of fuel to drill each one of these holes, and the amount of ice melted per hole is about 200,000 gallons. And the weight of the drill is 25,000 pounds, so it's really a formidable operation. And this is an example of a thermodynamics problem I gave to some students. I was teaching an inquiry-based class for elementary school teachers, where one of the activities they were doing was learning about thermodynamics, melting ice, measuring the phase transition energy and heat capacity and various things for ice. So this is a real-world thermodynamics problem I gave them. I said, when Dr. Hoffman went to the South Pole, she was only allowed to take 2 2-minute showers per week, which is one of the downers. And it says, why are they? I asked them, why are they so stingy with water at the South Pole when there's frozen water all around you? It says, you see, all the water at the South Pole is frozen, so never in recorded history has it gotten above freezing. The only way to get water is to melt ice, and a little scarce because it all has to be floated by plane. So I had them calculate how much energy it took to melt. To heat, first of all, heat the ice up to where you can melt it, and then melt the ice into water. And then I asked them, well, why is it that we actually get to take warm showers and not cold showers? And I asked them to show it really takes relatively little energy once you get through that phase transition to actually get it to body temperature. It's a drop in the bucket. So yeah, this is a warm shower. It doesn't last nearly long enough. Another thing that I think connects to undergraduate physics is how a photomultiplier tube works. This is all, of course, just a photoelectric effect. This is a very, IceCube at its core is just a very simple detector, right? So you just have, it's very easy to understand. You just have a photon coming in, and then you start a chain reaction, and it gets accelerated by electromagnetic fields. And then so you can see even the dimmest light in the photomultiplier tube. Of course, IceCube's instrumentation is, in reality, a lot more, there's a lot of bells and whistles built around this very simple piece of instrumentation. Water, of course, expands when it freezes, so this has to go in a deep glass pressure sphere of the same sort that they used for the cameras that explored the Titanic. Because at the bottom of these holes, due to just the pressure of the column of water above it, and the fact that it has the top refreezes first because the surface is the coldest. Ice turned out to be a great thermal insulator. I guess that's why it work. But there's really a lot of pressure at the bottom, so our design pressure was about 300 atmospheres. So it really has to survive quite a lot of pressure. But luckily, although water and electronics don't get along, water and ice don't mind each other that much. So if you just wait long enough and things will freeze, sometimes things start changing again. So we also have very long cables going to the surface for some of these. And there's a lot of dispersion. And if you want to track a muon through the ice, you really want to know very precisely the timing and the location of these optical modules. So we actually digitize the entire waveform in the ice there. And we also have an ingenious way of actually overcoming the cable dispersion and giving an accurate timestamp. So we have a computer on the surface that generates a waveform, sends it down to the optical module. The optical module has identical electronics and produces the same waveform and sends it back after some pre-programmed delay. So you can compare peak to peak or trough to trough or two, even though the wave gets very dispersed. You can compare like features on that waveform and get an accurate round trip time calibration for each of your optical modules. So the other thing we have to do to really understand what's going on is each of these optical modules is equipped with some little lights, LEDs, and that's used for various diagnostics. And it also is used to actually see where our detector landed. So you can flash these LEDs and see when the neighboring optical modules see that light, and then you can calculate the distance between the two. So they're normally 17 meters apart, but we had one kind of messed up one, but the manufacturer kind of screwed it up, and there was 16 alternating 16 to 18 meter spacing, and you can see that we clearly see that. And we can use a similar technique to see. We can use a similar technique to see on neighboring strings how far apart by just spinning a parabola, see how far apart the neighboring optical modules are, and we can get a pretty accurate measurement of that. So here's a picture of the deployment. So you can see this is an optical module getting attached to the IceCube cable. That's me right there, working very hard. And this is a picture of the cable with the optical module attached going down the pole. Now, I don't have time to really talk too much about this, but I would like to mention in passing, because I'm coming right after Greg, that IceCube also has an associated air shower tank that's very much like OJ on the surface called IceCube. This is for two purposes. One is that it turns IceCube essentially into a three-dimensional air shower array. And the other reason is because what's coming from the atmosphere is actually background for us. We're really looking at neutrinos coming directly from the source and not produced in the atmosphere. We can use that as a veto as well. So on top of each of these strings, there's two of these J-style tanks. Okay, so here's a picture of IceCube, and of course, the properties of the ice for us are very important. Francis Halsen, the father of IceCube, likes to say, we don't have the detector we built, we have the detector God gave us. And so we have to understand it very well, and it turns out our very first refereed publication was in a journal of glaciology, and we actually put a laser down the hole and measured what was getting backscattered into one of these drilled holes. And you can see that we made an excellent, very precise map of the dust concentration. So this corresponds to about 70,000 years ago. There must have been one hell of a volcano or something around there. And we have a very opaque layer. And this here is what a 500 TeV air shower looks like in our three-dimensional IceCube detector. So you can see it's coming in, it's lighting up all the surface tanks, and as all those muons that penetrate down the detector go through the detector, you can see that there's this area about halfway down the detector corresponding to this dust layer where it's basically opaque. So IceCube is sensitive to all neutrino flavors, and you can see here that it has the greatest sensitivity to muon neutrinos, which if you want to do astrophysics, muons have a large momentum and have a trajectory that don't bounce around like electrons do, so you get the most directional information from those. And I'll talk a little, and this is the energy over which you can actually see a muon neutrino. And so that's the energy range over which we can reconstruct them. And the reason for this, as I've already alluded to and was already mentioned by Greg, is because the muon, these are very, very high energy muons. They have, they're in their own clocks. They're experiencing current dilation or in our frame contraction. So this is the same reason that these cosmic ray muons reach all the way down to the bottom of our detector, is the reason that we can track the 1 TeV muon all the way through the detector. At 1 TeV, a muon has a track length of about 1 kilometer. If you go to higher and higher energies, you can have much larger track lengths. So actually, IceCube's effective volume, or the volume over which they can effectively see a neutrino interaction, goes up as you go to higher energies, because we could potentially see a muon that interacted kilometers away, but had a long enough muon track that it actually reaches our detector. Of course, the problem as you go to higher energies is that your fluxes drop off as well. So just to give you an idea of what we are challenged with here. So these things that are signal for gradient background for us are hitting our atmosphere and showering. And of course, the muons go hit the atmosphere. Many of them range out. Some of them are high enough energy that those hitting over our head actually reach our detector. There's also neutrinos being produced in our detector, and there's no way on a one-on-one event-by-event comparison we can say that one neutrino comes from atmospheric interactions versus a cosmic interaction, except to say that on the atmospheric, the energy of atmospheric neutrinos is expected to be much lower than it is for cosmic sources. So we can shield ourselves from cosmic ray muons by preferentially looking for muons that appear to be coming up through the Earth, because neutrinos can actually penetrate the Earth and go all the way through, but muons can't. The atmospheric background is completely irreducible. We have this hum from atmospheric neutrinos, and so we're really, in looking for correlating neutrino to a source, we're really looking for a fluctuation above background. And this really shows what we're dealing with. So this 1,000,001 background rejection. So you can see there's cosmic ray muons here are in the sort of cyan, and neutrinos are down here in green, and the total muons and neutrinos are in black, and then there's simulated, and this is IceCube data is in red. So what we need to do is we actually need to cut down this background. What about the direction? Well, a little bit of freshman physics again. For neutrinos at 1 TeV, the neutrino is going to be collinear with the daughter muon to within a degree, and that is just from conservation of momentum. We have a very heavy thing, right? And people always ask me about the Earth's magnetic field and how that, and how that impacts. At 1 TeV, it's insignificant. One of the first analyses we did with IceCube was the moon shadow. So because we have this, one way we can test the pointing resolution and the directional reconstruction capabilities of IceCube is because we're bathed in these this flux of cosmic rays, we could look in the direction of the moon and see if we could see the moon was shielding us from cosmic rays, and look for a deficit in the direction of the moon. So we confirmed the existence of the moon too. I think it's about 5 6 now. So we actually have made an astrophysical observation, something outside of our Earth. We're very proud of it. I should also say, for those of you who are familiar with Super K or whatever, that we do have energy resolution, because we are in a high enough energy regime that muons are no longer minimum ionizing. There's stochastics along the track, so we can actually make a crude energy estimation. And that's something that we can use to beat down this background of atmospheric neutrinos. So this is the challenge. This is a picture of events in IceCube. Only 1 in a million neutrinos are upgoing, and that is what we're looking for. So these are pictures of typical events, presumably cosmic ray muons going through the detector. And so these are some of our first upgoing neutrino candidates in the completed detector. So these are just from a few months ago. So in the last couple of minutes, I think I have just 5 minutes left or so, I'm going to say a little bit show a little bit of the results that we've gotten so far. There's a lot of astrophysics we can do with IceCube, and people are thinking of new things every day, because once you have a hammer, everything looks like a nail. So we can certainly do point source searches, as can OJ. We can look for gamma ray bursts, which are point sources, except they're transient. We can look for a diffuse glow of neutrinos. So we can just measure the flux of neutrinos at high energies and see if that correlates to what we're seeing in the cosmic rays. We can also look at supernovae, which is a little harder to explain because those are lower energy phenomena, but ask me about that at lunch. That's a little bit of a story. So this is a picture of our point source search. So at the end of the day, we make a map of the sky, and like I say, you can't say any individual neutrino is coming from a cosmic source. All you can say, because of this atmospheric background, all you can do is look for clustering of neutrinos. Now you'll notice that we show the southern sky, which is directly overhead, as well as the northern sky, even though I said we use the Earth to shield us from cosmic ray muons. And the way that we're able to do that is that we're able to use those energy reconstructions. So we can actually use these energy variables to beat down the atmospheric background overhead, but we have a higher energy threshold in the southern hemisphere. So far we haven't seen any statistically significant clustering, but this map is made with just the first 40 strings of the detector. And I'm going to jump ahead in the last few minutes. I'm going to say a little bit about the particle physics we can do with IceCube. So IceCube is not only the world's largest, well, it's not the world's largest telescope, because I think OJ points that. But not only is it a large telescope, but it's a world's largest neutrino detector. Or Cherenkov detector, I should say, because you can see other things besides just neutrinos. You can see, for example, magnetic monopoles, anything that's will ionize and produce Cherenkov light. So one thing that's really of interest that's come up in this conference a few times is the search for dark matter. So the way IceCube can see dark matter, which is a little indirect, is that the sun, which has been traveling through our galaxy for all this time, is a gravity well, and one would expect that as it went through as it's revolved around through our galaxy, it's kind of swept out some dark matter and it got trapped in the gravity well. And these particles, these dark matter particles can annihilate with each other, and at the end of the decay chain you get neutrinos. So if you have dark matter annihilating in the sun, you would expect the sun to be an apparent source of relatively high energy neutrinos, so higher energy than would come from the fusing reaction. And this is a complementary search to the direct detection experiments because a lot of the cross sections are spin-dependent, and the sun is primarily a proton source. And that's one of the ways where our new deep core enhancement comes in. The sun gets maximally 23 degrees above the horizon, so we're really looking for horizontal particles. And they're, on average, much lower energy than the astrophysical neutrinos that we're looking for. So what we can do is we can look for particles that start and stop in the detector, and we can use IceCube basically as in vitro and use this denser instrumented central region to see the lower energy neutrinos. So it works basically like this. If you had a cosmic ray muon coming in, it looks like travels straight through your detector. But if you had a low energy neutrino that came in and interacted in the detector and had a relatively short track, you could see it start and stop and start and range out in the detector, and you can use that to be down in that. So that brings me, right, that's 50 minutes. Okay, so that brings me to my concluding slide. So IceCube was completed this year after 6 years of construction, so we're all very excited. Many of the analyses from the 22, 40, and 59 string configurations are complete, and that's because, unlike the old days when we were flying data out on tapes, we're actually sending things by satellite now. So we're actually not able to analyze data in real time, but at least within a few days we can handle the data. We're continually refining our analysis techniques where our sensitivity has exceeded the design goals. And we have this low energy enhancement. One thing I didn't mention, but you can ask me about it once if you want, is I'm one of the principal investigators on a new telescope that began construction last year at the South Pole called the Stereo Radio Array, and that is going after GZK neutrinos. So neutrinos from the GZK interaction with the protons interact on a cosmic microwave background. And that uses a different detection technology altogether because the optical Cherenkov technology was just too costly to scale up to something as large as what we need, and we hope that phase 1 will be funded for 100 square kilometers, so that's what we're looking at. So we're having our second construction season this coming year. So, thank you.